Hello, fellow number enthusiasts. Today, I want to take you on a journey through the fascinating history of number systems. From the ancient civilizations of the Mayans, Babylonians, and Egyptians to the present day, we'll explore how numbers have evolved and the different systems that have been used throughout history. So, buckle up and get ready for a wild ride. Let's start at the very beginning. The earliest known number system was developed by the ancient Mayans. They used a base 20 system. That's right. They counted in 20s. Can you imagine going to the store and buying 60 tomatoes? That's just 3 Mayan tomatoes. Anyway, the Mayan number system was a combination of dots and bars, with each dot representing 1 and each bar representing 5. But what's really impressive about the Mayan system is that they also developed the concept of zero, which was represented by a seashell. That's right. The Mayans were the first civilization to use a symbol for zero, which revolutionized mathematics and paved the way for the development of modern number systems. These are some symbols used by the Mayans to represent the numbers from 0 to 19. Moving on to the Babylonians, who used a base 60 system. Yes, you heard that right, 60. This system was based on the number of digits on one hand and one foot, which makes sense when you think about it. The Babylonians used a combination of vertical wedges for the numbers 1 to 9 and diagonal corner wedges to represent the number 10. They then combined these symbols to represent larger numbers, with each position representing a different power of 60. You can pause the video and take a screenshot of this. This base 60 system is still used today in some fields such as geography and time measurement, where degrees, minutes, and seconds are used, and in music where 60 beats per minute is a standard measure. And if you think that's confusing, just wait until we get to the Egyptians. Now let's talk about the Egyptians, who used a base 10 system like we do today. However, their number system was much more complicated than ours. They used hieroglyphs to represent numbers, and each symbol had a different value depending on where it was placed in the number. For example, the staff was used to represent 1, the heel bone represented 10, the coil of rope represented 100, the lotus flower represented 1,000, the pointing finger represented 10,000, the tadpole represented 100,000, and the astonished man represented 1,000,000. These hieroglyphs were used in combination to represent larger numbers. And if that wasn't enough, the Egyptians also had separate hieroglyphs for fractions, which made their number system even more complex. It's amazing to think about how the Egyptians were able to use such a complex system to perform calculations. However, it's safe to say that we're all grateful for the much simpler number systems we use today. Imagine having to do long division with hieroglyphs. It would certainly take a lot more effort than just pulling out your calculator. Now let's fast forward to the present day and talk about binary, octal, and hexadecimal. These number systems are used in computing and are based on powers of 2. Binary is a base 2 numbering system that uses only 2 digits, 0 and 1. Each digit in a binary number is called a bit, and the value of each bit is based on its position in the number. While binary may seem limiting compared to the base 10 decimal system we use in everyday life, it is incredibly powerful in computing because digital devices can represent and process information using just 2 states, on-off, or true-false, which correspond to the 0 and 1 digits of binary. Computers use binary code to represent letters, numbers, and even images and sounds by encoding them into sequences of binary digits. But how does it work? Well, it's all based on powers of 2. You see, in the decimal system, the one we humans use, we have 10 digits, 0 to 9, and each digit represents a power of 10. For example, in the number 1, 2, 3, the digit 3 represents 10 to the power 0, the digit 2 represents 10 to the power 1, and the digit 1 represents 10 to the power 2. In binary, it's the same concept, but with only 2 digits, 0 and 1, and powers of 2. So let's take the number 101 as an example. We can break it down like this. Each digit represents a power of 2, starting from the rightmost digit, which represents 2 to the power of 0, which is just 1. The next digit to the left represents 2 to the power of 1, which is 2. And the digit to the left of that represents 2 to the power of 2, which is 4. So when we add up the values of each digit, we get decimal number 5. See, not so hard, right? Now let me give you a little cheat sheet with the powers of 2, so you can impress all your friends with your binary skills. And there you have it, binary in a nutshell, or in a table, I guess. However, binary can be quite difficult for humans to read and work with, which is where octal and hexadecimal come in. Octal uses 8 digits, 0 to 7. Each octal number can be represented using only 3 bits, with each group of bits having distinct values between 000 and 111 for 7. This makes it easier to read and work with than binary. But it's still not ideal for many applications. That's where hexadecimal comes in. It uses 16 digits, 0 to 9 and to F. Each hexadecimal number can be represented using only 4 bits, with each group of bits having distinct values between 0000 and 1111 for F, that is 15. This allows for even more compact representation of binary data and makes it much easier to read and work with than binary or octal. Now you may be wondering why we needed hexadecimal and octal in the first place. The answer lies in the way computers store and process data. Computers use binary code to represent all data, but it's not practical for humans to work with binary code directly. So we needed a way to represent binary data in a more human-readable format. Octal and hexadecimal were invented to solve this problem, and they've been essential tools in computing ever since. And if you're wondering why A to F are used in hexadecimal, it's because we needed 6 more digits and didn't want to invent new symbols. So we borrowed letters from the alphabet. Hey, don't judge. It works. It seems we've reached the end of our journey through number systems. But fear not, fellow number enthusiasts, for there's always more to learn. In fact, understanding number systems is a crucial foundation for learning about logic gates and digital electronics, which form the building blocks of modern computing. So, if you're interested in learning about digital electronics and how logic gates are used to build circuits and perform computations, be sure to check out my next video, where we'll explore the fascinating world of logic gates. Until then, keep on counting, calculating, and never stop exploring the wonderful world of numbers and digital electronics. Thanks for joining me on this journey, and I'll see you next time.